So in last lecture, we learned about some of the key terminologies about the inferential statistics, like what is hypothesis, what is research hypothesis, what is estimation, confidence interval, level of significance, types of error. So in this particular video, we are going to learn about a process of hypothesis testing with an example. So let's start learning about the process of hypothesis testing. So generally, hypothesis testing is a six-step process which start with establishing a hypothesis. So whenever a researcher has some hypothesis in mind, he need to reframe it into a statistical hypothesis by stating the null and the alternate hypothesis. Once he is done with statement of null and alternate hypothesis, second, he need to determine the appropriate statistical tool or test according to the sampling distribution. Once he determines which test will going to be applied on the collected data, third step during the hypothesis testing is to specify or determine type 1 error rate, which is generally denoted by alpha and also known as level of significance. Once you have decided the level of significance, the next step is to calculate the value of test statistic. That means if your test statistic is Z, then you need to find out the calculated value of Z. If your test statistic is T, then you need to find out the calculated value of T. Once you are done with the calculation of value of test statistics, then you need to decide and determine the decision rule. That means what will be the rejection region and what will be the non-rejection region. On the basis of that, you may be able to reach at the statistical conclusion. So these are the very easy six-step process which we need to follow while testing any hypothesis. So let's discuss each step in detail with an example. But before that, one of the very important part of the statistical hypothesis testing is to determine statistical test. So in the inferential statistics, generally there are two types of tests. We can classify tests into two types. One is called parametric test and second is called non-parametric test. So we cannot directly apply a parametric test on any data which are quantitative in nature. To apply a parametric test, it needs to fulfill some of the assumptions. So what are the assumptions to use a parametric test on a data? The first assumption is that data should be normally distributed. So first step as a researcher, what we need to do that whenever we collect the data, even though it is a quantitative data, we always need to check for its normality. So you can use any of the statistical software to check whether the data is normally distributed or not. If the data is normally distributed, then second assumption which we need to check is whether the variance is homogeneous, that means equal or not. If the variance is also equal and if the data which you have collected is of interval or ratio kind of a data, then you can go ahead and use any kind of parametric test. Whereas in case if your data is not normal or your variance is not equal or your data is not interval or ratio in nature, you can go or use non-parametric test on a data which you have collected. So these are the requirements for non-parametric test. Data may or may not be normal distributed. It doesn't require a variance to be homogeneous, and you can also apply any kind of non-parametric test on nominal or ordinal kind of a data. So commonly used parametric statistical tests are Pearson correlation, then Z-test, T-test, one-way ANOVA, paired T-test, and repeated measures ANOVA. Whereas commonly used non-parametric test includes Spearman's correlation, Mann-Whitney U-test, then Kruskal-Wallis test, Wilcoxon sign rank test, and Friedman test. So this is the first step, how you can determine about these statistics. There are various methods to determine which test will be applied. Like in the another slide, we will also learn that how the process of inferential statistics. So for example, here we can see that what kind of data we have collected. First step, we can go by this approach as well, flowchart approach, that what data we have collected. Is it a frequencies or it is a measurement? If it is only a frequency, then what is our objective? What kind of test we want to apply? Whether we want to compare the observed count with the theoretical count, then we can go for chi-square test. Whether we want to test the difference between the counts, again we can go for a chi-square test. If we want to test the association between the group of counts, then again we can go for chi-square test. Same way, if we have measured the data, then what kind of test we want to apply? That means whether we want to test a difference between the sets or we want to test a relationship between the two sets. If we want to test a difference between the two sets, means if you want to compare two means, if you want to compare the more than two means from more than two different populations, or if you want to compare two different proportions, or if you want to compare two different variances, then we can go with this, like again we have two sets or more than two sets. If you have two sets, then again you need to check for whether the data is normally distributed or data is not normally distributed. In case your data is normally distributed, then again you can see that if it is a paired test or if it is an unpaired data. If it is an unpaired data, then you can go ahead with the t-test. If it is a paired data, then you need to go for paired t-test. Same way, if your data is not normally distributed and the data is from two different sets of population, you can go and use Mann-Whitney U-test. If data is of quantitative nature and if your data is from more than two different population, that means three population, four population, or more than four population even, then you can use ANOVA test. If you have more than two sets of data, that means if you have more than you have collected data from more than two different population, that means three or four or five different population, and if your data is not normally distributed, then you can go for Kruskal-Wallis kind of a non-parametric test. Same way, if you want to test the relationship, you can go for test of correlation. Again, you need to check for normality assumption. If it is a normally distributed and quantitative data, you can go for Pearson correlation coefficient test. If it is a not normal data, then you can go for Spearman coefficient correlation test. If you want to find whether there is one factor affects another, right, or whether one variable can be a good predictor for another, then you need to go for the linear regression analysis. So this is another method how you can approach to identify that what kind of test will going to be used for the data which you have collected. There is one more flowchart which I'm going to share on a Canvas platform, which you can refer to identify that which particular statistical test is going to apply on the data which you have collected. So let's take an example. So we are going to test the hypothesis, and we are also going to learn about the entire process by taking this example. So in this, the Food and Nutrition Board of National Academies of Science states that the recommended daily allowance, which is denoted by RDA, of iron for the adult females under the age group of 51 is 18 milligrams. To test whether every woman under the age group of 51 is getting this recommended daily allowance of iron or not, National Academy of Science have collected a sample of iron intakes from the 45 randomly selected adult females of the age group which is under 51, and then calculated the sample mean, and they found out the value of the sample mean is 14.68 milligram. So we want to test that at 1% level of significance, thus the data suggests that adult females under the age group of 51 are on an average getting less than recommended daily allowance of 18 milligram of iron. Further, the data, one more data has been given that assumed population standard deviation is 4.2 milligram. So from this data set, we can identify that we want to test a null hypothesis that whether all the females which are under age group of 51 is getting a daily recommended daily allowance of iron which is equals to 18 milligram, and we want to prove that no, they are not getting the recommended daily allowances of 18 milligram and they are getting less than recommended daily allowance of 18 milligram. Further to this data, the size of sample is 45 and the population standard deviation is also given, which is 4.2. So from this, the first step is to state the null and the alternate hypothesis. So null hypothesis here, it will be that mu equals to 18 milligram An alternate hypothesis, since we want to prove it is less than recommended daily allowance, so alternate hypothesis will be mu is less than 18 milligram, right? Further, if you want to check from the previous chart whether if the data is normally distributed, this is for one group hypothesis testing. If the sample size is greater than 30, then we can use which test? Z test. So in our case, the sample size is 45, which is greater than 30. Data is normally distributed because we already have a population mean and population standard deviation with us. So we can go for Z test. So we are through with the first two steps. So here we have this much data which is available. Further, the level of significance here in the data which has been given is 1%. So alpha is also 1%, which has been stated here. So we can go step by step. The null hypothesis, as I have stated, mu equals to 18 milligram. Alternate hypothesis will be no, they are getting less than recommended daily allowances. That means mu is less than 18 milligram. And since it is a left tail test, so we will going to scratch the probability of having a two tail test or right tail test. Then we have also decided the level of significance, which was already given, that we want to test this hypothesis at 1% level of significance. We have also identified that which test statistic will going to be applied. So here we are going to use Z test, and the formula for Z test is x bar minus mu x bar. That means sample means minus population means upon error, which is sigma upon under root n. So by putting all this value, we will get the calculated value of Z, which is minus 5.30. Now we need to set a decision rule that for one tail test with 1% level of significance, which is a left tail test, we need to identify what is the value of Z statistics, right? So in next slide, we will see that. So it is a left tail test, and at 1% level of significance, that means 99% confidence interval, we will get the value of Z from the table, which is 2.33. So our rejection region will be just only one side. That means left side, and the value at this particular point, which is called a critical value point, is minus 2.33. So we have set the decision rule that if our calculated value of Z is less than minus 2.33, then we will reject the hypothesis. If the value of calculated value of Z is larger or greater than minus 2.33, that means it falls in this particular region, which is called non-rejection region, this entire region, then we will fail to reject the null hypothesis. But in our case, the value of calculated value of Z is minus 5.33, which is less than minus 2.33, which is less than minus 2.33, and it will fall somewhere around this rejection region, somewhere around here. So definitely we are going to reject the null hypothesis. So that means we can make a statistical conclusion on the basis of the above statistical test that at 1% significance level, the data provides sufficient evidence to conclude that adult female under the age of 51 are on an average getting less than recommended daily allowance of 18 milligram of iron. So this is how we can go ahead with the process of hypothesis testing. So let's see that if you are using Excel or other statistical software for hypothesis testing, then how we can interpret the output. If you are generating the output or testing the hypothesis with some of the software, you must know how to reject or accept the hypothesis based on p-value. So this is the rule to accept or reject null hypothesis based on the p-value. If the p-value is less than value of alpha, that means level of significance, reject the null hypothesis. If p-value is greater than equals to alpha, then accept the null hypothesis. So this is one of the output of Microsoft Excel. Here we have compared the two means. So you will get the value of mean, variance, what are the total number of observation in population sample 1 and sample 2. Then this is the T statistic, that means calculated value or test statistic, which is called calculated value of T, which is 1.82. But here we do not want to compare with the critical value. Here we just want to make decision based on the P value. So here you will observe that there is a value which is called P one tail test and P two tail test. So in this case, if this hypothesis testing is for one tail test, then here the value of P is 0.03, which is less than level of significance 0.05. So on the basis of this particular P value, we will decide to reject the null hypothesis. But at the same time, for the same data, if it falls to be a two-tailed test, then the value of P is 0.07, which is greater than 0.05, which that means 5% level of significance, and we may decide not to reject the hypothesis and accept the null hypothesis. Similarly, this is an output of SPSS. Here you can see that significance two-tailed test. This is an output of two-tailed test. So the value is 0.000, which is less than level of significance 0.05, right? So we decide to reject the null hypothesis. So this is how, like, again, you can interpret the output which was generated by statistical software and decide whether to accept or reject the hypothesis. I hope that now the process of hypothesis testing is clear to everyone. If you have any query, then you can drop me an email on my email ID chintan.rajani@rq.ac.in. Thank you.